Newport Beach Public Library Foundation's roster of outstanding programming, which brings us together to hear from the world's leading authors, artists, journalists, and scientists on topics of interest, relevance, and importance to our community. Before we begin, I'd like to ask everybody to silence your cell phone. I made sure mine was off. And we're going to hold questions to the end. We'll have a Q&A with Park afterwards. So Spotlight on Science is actually one of 6 programs that the Library Foundation offers to this community. The Woody Lecture Series showcases distinguished speakers. Library Live brings authors of renown to the library. The Financial Literacy Workshop provide up-to-date information on managing your money and your estate. Medicine in Our Backyard, we had one of these just the other evening, highlights the latest in health and medical advances. And the book discussion group is a lively conversation on the books of great interest and acclaim. Now, the Library Foundation also supports innovative library resources like the Media Lab, self-checkout computers, the tech toys, the Wayfinder, and the eBranch of digital resources. It's through the generous support of the Foundation members that this is all possible. So as we near the end of the calendar year, we urge you to make a contribution to the Foundation and renew your membership or become a new member. We just cannot present these many programs or fund important resources for this library without your support. So last night we had an exciting meeting at the City Council where we found we would be progressing forwards on the building of Woody Hall. So please, applause. But the point is that both last week's Steve Lopez Library Live lecture, hopefully some of you were here, and tonight's event have filled this room to capacity and sometimes beyond. This multi-purpose room has limited occupancy, sightline, not from here, it's actually a pretty good sightline from this side, and audio limitations. And our audience always reminds us of this with the surveys. The Sunday musicals, the children's programs like the Holiday Nutcracker, and other community programs that use this room face the same drawbacks, which is why the Foundation accepted a huge challenge to raise 50% of the funds needed to construct a state-of-the-art library lecture hall, really a civic auditorium for the Newport Beach community. Now called Woody Hall in recognition of a generous gift by Bill Woody and Keiko Sakamoto, whose family have been library support leaders for many decades. It will truly become a community asset, as we say, beyond books. We urge you to join us in making this vision a reality as we broaden our fundraising outreach over the coming months and years. So let me make a comment about tonight's program. Hopefully some of you may have attended our initial spotlight presentation from UCI Dean James Bullock in April this year on the James Webb Space Telescope. How many of you were here at that? This is great. Well, this was incredibly well received and in fact is the impetus for this program this year and incentivized us to broaden the program. So together with my co-chair Bruce Clark, and on behalf of the entire committee who are in the front row here and the Foundation Board, many of us here, we are excited to introduce the 2023-24 program, which will bring us 3 fascinating presentations on a topic on everyone's mind, artificial intelligence, or AI. Now, while many of us may have read about or already experienced the impacts of recent advancements in AI, such as ChatGPT, the broader areas of machine learning, or big data as it's been called, have been widely utilized across the scientific disciplines for many decades, actually. In fact, it is these foundational developments, when combined with more recent advancements in computing power and speed, which have brought us to this inflection point, or you might say event horizon, in AI. So, tonight's speaker is Dr. Padhraic Smyth. He will help us understand what the term AI means when taken in the context of scientific discovery and how it's helping advance and accelerate our understanding of everything. And that could be the body, the planets, the cosmos, and our society. Our subsequent programs, which will be on March 20th and May 15th, will cover more specific topics on the impact of AI as applicable to climate change on the planet's glacier planet's glaciers, on our coastline, and so please mark your calendars for those events. Dr. Smyth is a distinguished professor in the Department of Computer Science at UCI. He's published over 200 papers on machine learning, artificial intelligence, and pattern recognition, and is the founding director of the UCI Center for Machine Learning and Intelligent Systems. He has received research funding from NASA, Google, Qualcomm, Experian, and consulted with Samsung and AT&T, among others. Few people are more qualified to talk to us about the future of artificial intelligence and its impact today. Please join me in welcoming Dr. Smyth to our library.
Thank you very much for that introduction. Before I start, I wonder if there's possible to get the laptop in front of me. I should have thought of that before, but great, thank you.
I'll grab that.
Right, thanks. Perfect. All right, we've got to get the AV set up. So thank you very much. I'd like to thank the Foundation for inviting me to speak. Really an honor. And coming out of the academic world to speak to the real world it's a great pleasure, and to tell you what we're doing there in the Ivory Tower. I'd also like to thank whoever arranged the weather. I'm originally from Ireland. Padhraic is an Irish name, and I feel really at home tonight because this would be a nice summer's day in Ireland, as my wife and two sons who have visited Ireland many times will tell you. All right, so tonight we're going to talk about AI, and as I get started, I want to acknowledge that what I'll be talking about is built up on knowledge from many students I've worked with at UCI over the years, and various collaborators at UCI and Caltech and JPL and other places. Also various funding agencies like the National Science Foundation who fund our research, and I'm very well aware that National Science Foundation, National Institute of Health comes from taxpayer dollars, all of you supporting the research that we do at universities, and we're always grateful for that. Full disclosure, as was just mentioned, Randy mentioned, I have gotten funding from industry, so I may say positive things, I may say negative things about industry, but just be aware, full disclosure, I work with industry quite a bit, so just keep that in mind. For the next 40 minutes, what I will try to convey to you is what is AI, what is machine learning, how do they differ, what are some of the basic concepts. There's a lot of media hype about these areas, but I'll try to give you from my perspective as a technologist what these things are sort of inside the black box to the extent that we can talk about that. I'll then move on to talking about AI and science, how AI is changing science. And again, as Randy pointed out, it's actually AI has been helping science for many years, but it's just become kind of more prominent now. It's accelerated, if you like, in the last few years. And I'll also talk about, there's a lot of promise, but I will also add some, there's peril as well. There's danger here. AI can do a lot of positive things, but it also has some blind spots and limitations. And again, the media and the companies don't always, that might be the first thing they want to tell you. They first want to sell you the software and then later on tell you what it can't do, for example. Okay, so let's start off with what's artificial intelligence. Well, there's two words here, non-human artificial, so that usually means computers. And then intelligence, well, we could talk all night about, what that is. Human-like behavior, maybe in some domains like game playing or doing calculations better than humans and so forth. So even the term AI is a little nebulous if you want to pin it down. But after World War II, we had, computers, large scale. People started to think we could make these machines do interesting things. And so AI was founded in the late 50s. Various academics and people like Claude Shannon and so forth got together. And the early days was pretty much what's called formal AI. So writing down, these people say, we're smart people. Let's write down what the rules of common sense are. We'll put them in a computer program. The program can make deductions, and it can predict things using, chains of reasoning, so a lot of logic, a lot of rules, trying to design general thinking machines. Some very smart people, some really creative work, but it didn't work. And so the question we might ask is, why didn't this work? And the reason it didn't work, and we were talking a little bit earlier, is one of the reasons that things like autonomous vehicles are very hard to get to work in a general sense. There's just so many exceptions. The world is a messy place. If you try to write down general rules for things like time and physics and so forth, it's actually a lot harder than you might think. So this other aspect of AI, and this is actually a technical term, scruffy AI, and I'm part of the scruffy AI crowd, full disclosure, said, well, this doesn't seem to be working. So, from about the 1990s onwards, this became more popular. Looking at the real world, at measurements, we now had more sensors, more digitization, looking at data, look at things like speech and images. Forget about big general reasoning for the moment. What could we recognize speech? Could we classify images? And started to see some success there. So a little bit more bottom up, if you like. Recognizing that things like uncertainty and probability are actually really important if you want to build an intelligent machine. And then one of the areas that emerged, and actually UCI was very prominent in this area, going all the way back to the 80s, 1980s, is machine learning, which I will describe to you at least at a high level in the rest of the talk. Terminology, so I think, again, it's confusing. There's AI, that's kind of the big umbrella, if you like. And then within AI, you have machine learning, which is like a balloon that started out kind of small, but's been expanding, so that now the two terms, machine learning and AI, are somewhat synonymous. But AI is kind of general intelligence. Machine learning is a more specific technology that is taken as effectively doing AI currently. And then within machine learning, you have these things called deep neural networks, and I'll show you some examples of those. That's a particular machine learning technique, and again, it's like, imagine a balloon that's expanding. It's kind of taking over all of machine learning, for better or worse. The deep neural networks have a lot of advantages, but they also have blind spots, as we will see. And then we'll talk a little bit about two particular types of deep neural networks that are the basis of most of the AI machine learning applications that you see. These are classifiers and generative models, and if that doesn't make total sense yet, don't worry. We'll have examples and so forth as we go. And I will probably refer interchangeably to these terms going along. I'll talk about models and neural networks and machine learning, but really, they're all the same thing, in effect, from the perspective of tonight's talk. So let's start with a black box, a model. And it's going to take some inputs. These will be numbers, and it's going to produce an output, which is going to be another number. So this is the basic concept of machine learning 101. And of course, instead of just 4 inputs, we might have a lot, and we might have more outputs. One of the things that students, when they take our classes in machine learning at UCI, they're a little bit disappointed to find out that this thing is actually, it's all mathematics. This is a mathematical function. It's defined as the output is a function of the inputs, and it has these weights or coefficients that determine, if you like, the shape of the function or what the function actually does. So one of the things that's kind of interesting is that all that mathematics that you learned, way back when, is actually very useful for understanding machine learning. Ideas like calculus and linear algebra and probability come up over and over again. So you have these weights. They're computing weighted combinations of the inputs and then going through these intermediate nodes and computing more weighted combinations and eventually producing a number at the output. One of the key things is that these weights are learned. This is the learning part of machine learning. So we're going to show it inputs and show it outputs and say, try to predict the output given the inputs. And I'll show you how that works with images in a few minutes. Let's step back and go to an even simpler model. Forget those intermediate nodes, if you like, in that picture we had before. This, some of you might recognize, is essentially a weighted sum. It's a classic, it's a linear model, beloved of statisticians for years, well known, and the connections between statistics and machine learning are very, very close. In a sense, statisticians are very careful about what they do, and machine learners just say, let's just try it and see if we can, if it works. And of course, this goes way back to at least Gauss, if not before, who figured out how to get the weights for a model like this, and he was looking at asteroids, and this is his famous treatise on orbiting objects. It's 223 pages, and you can buy the English translation on Amazon, actually, if anybody's interested. Quite a read. So, going in the wrong direction here. Fast forward from 1809 to about 1960. Now you had computers. So Gauss was doing all this by hand. But with computers, you could actually do this on a larger scale. So one of the very first applications of machine learning, if you want to think of it that way, was actually credit scoring. And in particular, 2 statisticians up in the Bay Area formed the Fair Isaac Corporation. And so our FICO scores are essentially started off as like income, debt, age. You need an intercept term. That's what the +1 is. And so some linear combination of those. Now, today, they're probably using other things, but for many years, this was the basis. And doing this on a very large scale with maybe hundreds of thousands of individuals like us using our own data, fitting the model maybe with hundreds or thousands of variables. And so from then on, people were interested in these kinds of ideas. And keep in mind here that these weights, the blue lines, these are in general are unknown. You're given a data set and you need to figure out what the weights are. So sounds very much like statistics, but it's going to be scaled up in a lot of ways. And here we have, this is my only equation, I think, tonight. We have an alpha and a beta and a gamma. I'm a professor, so I have to throw some Greek letters out into, all right. That's just a linear weighted sum of the inputs. It's limited as a function, as a mathematical function. It can only represent certain types of things. So let's try to make the model a little more flexible. And we're going to add in this hidden unit here, and we'll add in another one. So imagine I had two Gausses, had time travel forward. And so there's a yellow Gauss and a blue Gauss. And blue Gauss comes up with one linear function, one set of weights. Yellow Gauss comes up with another one. There's a third Gauss cousin. They come up with the middle one. And we're going to combine their different linear functions together. They're all measuring sort of different linear combinations of the inputs and produce an output. So this model is more complicated now than just a single weighted sum. It has more richness to it. And just one bit of terminology, this middle layer here is referred in neural network terminology as hidden units. They're not at the input, they're not at the output, they're in the middle of the model. And what we're looking at here is a very simple neural network. If you were a student in 1980, you might see this in a class, 1985, 1990 certainly. We were working with these things. I was at Caltech at the time. There's a lot of excitement about building these things. And the reason they didn't succeed at that point is we didn't have enough data, enough computing power to really scale them up. People thought they were able to do amazing things. But it was 20 or 30 years too early. So now we have still a mathematical function. So neural networks are still mathematical. They're taking inputs, mapping them to outputs with, we could write down an equation. And the exact nature of the mapping is determined by these weights. So the weights are the kind of the holy grail here. We get the right weights, and we're in business. So that's where we're headed here. Now, you'd hear the word deep used. So previously, we had a single layer of hidden units. You probably can't see that at the back, but we've added a second layer here. So we've sort of taken the Gausses and their functions and put more functions. And we can keep going to the right there and making this thing deeper and deeper. So deeper is that direction. The idea is you're building sort of hierarchies of functions. I'll try to tone down the mathematical language in a few minutes because I can see some people are like, what's he talking about, all this stuff? It's nighttime, you know. But you get a very flexible family of functions. And the more complexity you get, the more data you're going to need to fit this thing, and the more computation it's going to take. So again, it took a while for that to catch up with being able to fit these models large scale. Okay, let's try to do something a little more practical here. Let's try to classify cats. Let's say we have images of cats and we have images of other animals, and we want to know, is this a cat or not? This was actually one of the first applications that got a lot of attention, Andrew Ng at Stanford with his cat classifier. So one of the things here is you might be wondering, how do we get an image of a cat in as numbers into this model on the left-hand side? Well, an image is just a bunch of numbers, and so we're going to arrange them in certain ways, but they're just the pixel values that you get off your camera or whatever. So we want to take in all the numbers corresponding to the image of some cat. There'll be lots of different cats, and produce a number at the output. Typically, we look at probabilities. What is the probability that this is a cat? And here, actually, this is not very good. It's saying the probability of a cat is 0.3, which means the probability of not cat is 1 minus that, 0.7. So we need to change the weight. So the idea here is we want to up the probability of cat, downweight the probability of not cat. So we adjust the weights. Now, how do you adjust the weights? There's all these different weights inside this black box. Little side note, and I know there's a fair bit of math here, but if you have kids or grandkids, one of the things that to get across is to really understand something like machine learning, you need to know your math. And so here, the adjusting of the weights is actually an application of calculus. A very basic application. It's computing derivatives of all of these weights at one time. And that tells us, it gives us a simple recipe for adjusting the weights. And this is used, we're going to use it with the cats here, but in the language models and the other things you're going to see tonight, they're all doing the same way of adjusting weights. It's the power of these methods, is that once you know how to do this, you can apply it to lots of different types of data. So we're going to adjust the weights, and that's been done with calculus. There's a formula that tells us what to do. Now the probability of cat has gone up. And let's see, this is a second cat, I think. I'm losing track of my cats here. So now we get a second cat, and we say, hey, let's even make it higher. We want to be 100% confident these things are cats. So let's further adjust the weights. Now we're at 0.9. We've seen 2 cats. That's great. Now this poor dog comes along, and he's classified as a cat, and he's not happy. So we need to adjust the weights now for the dog image. And again, we still may be correctly classifying the cats, but now we've also got the dog correct. So what the black box is effectively doing is trying to differentiate between cats and dogs, somewhere in the weights, in what's going on. Now, I've shown you 3 images. This would be done with, 3 million images, typically, something on that scale, all on a computer, the adjusting of the weights happening over and over and over again. In some sense, very brute force. There's not much sort of thinking going on. It's really basic math, getting the right outputs for the different inputs. We also need to know, by the way, what the labels are. Somebody needs to have sat down first, a human usually, and said, these are cats and these are dogs, because the model needs to know what the right output is. Is this actually a cat or actually a dog? I'll come back to that a little later. All right. So one question, a really interesting question, is what is being learned internally by these models? What are these little white nodes learning? And it turns out they're really hard to understand. At the front, they're kind of local spatial filters, if you like. They're kind of picking up edges and textures and things. But then you go to the next layer, and it's now functions of the things that were at the first layer. There's a lot of research on this, and I can tell you it doesn't really give us insight. So the black boxes really are black boxes. And this is one of the issues with a lot of machine learning at the moment is it's very hard to look inside the black box and know what's going on. And so that's just something to keep in mind. And I don't think it's going to change significantly. These are just fundamentally, kind of mysterious to us in terms of we can look at them, but how would you explain those patterns of what it's doing? It doesn't tell us. It doesn't look like parts of a cat or anything like that. So, and this is typical. All right, so we can go beyond images. Actually, one of the very first successful applications of machine learning was spam email. Up at Microsoft Research, colleagues of mine, David Heckerman and Eric Horowitz, sat down and they figured out how to do this, and it was a real success. Speech recognition was another area where we can use these things, and now you'll see there's more than 2 outputs because we want to recognize all words in a vocabulary, so you get a whole set of probabilities that sum to 1, from most likely to least likely. And you can scale up. So the last 20 years or so, people have been scaling these ideas up with images, text, speech, sensor data, and using the same algorithms, adjusting the weights to get the right output, the same calculus-based ideas. You could have millions of inputs. As you start building these things, you end up with billions of weights. So something like ChatGPT will have billions of weights. Nobody knows exactly how many, and multiple outputs. So these things can get quite complex in terms of the code implementing them, but the underlying principles are actually quite simple. This is looking inside actually a very simple neural network, just different layers of different things going on. This one on the right is turned around, so the inputs are at the top, and this is from Google. It had 27 layers. I'm just showing these to give you a sense of, my little black box is just for illustration, but the real ones are much bigger, but still based on the same principles. So in the academic world, we like to build test beds so we can evaluate systems. So the ImageNet test bed was constructed around 2015. Alex Berg is a colleague of mine that we just hired at UCI. He was involved in this. And this had 1,000 classes. It shouldn't say 1,000 of, but 1,000 classes, millions of images, very hard problem. And when they started off on the left-hand side of this graph in 2011, accuracy was about 50% with state-of-the-art systems. By now, it's not perfect, but it's up around 90%. And this has been basically using more data to build more complicated models. And a lot of this is what has attracted the attention of industry. So around about 2013, 2016, companies like Google and OpenAI and Microsoft started saying, there's something going on here. These things are actually working a lot better than they used to in the past. And so that accelerated then the development of these types of things. Before 2010, the way we used to do this was we would do what's called feature extraction. We'd sit down and I've spent half my career doing this, try to figure out, could we come up with some kinds of cat-like features? Okay, let's detect an ear, let's detect a mouth, the whisker, we'll design a filter to do that. Same for speech, same for text. And then we put that through a classifier. So this 2-stage approach, very inefficient. And what the neural network is doing is essentially learning some representation of the inputs all the way through. So we can get rid of that feature extraction part that was common in pattern recognition, and now you can go from pixels to a decision, a prediction in one model. And this has been a huge shift in how we build these classifiers, pattern recognition systems. So with this, people were able to then sort of get on the engineering side and say, hey, let's build bunches of things that can look at images and move around and detect horses and buses and people and multiple things in the same image, apply them to medical data, a lot of screening, biopsies, and so forth, commonly use these automated classifiers. Autonomous driving is a hard one because you can get 95% of the way there, and as Tesla is finding out, the last 5% is really hard. There's just so many exceptions. So it looks very promising at the beginning, and you get lots of investors, and then it's like, this is harder than we thought. And so you look at things like pedestrian detection, and not quite there. There's street signs, these are all classified as pedestrians by this classifier. So the red boxes are supposed to be, parts of trees and so forth. So just be careful walking out in front of a Tesla. Okay, and other companies as well, not just them. I don't want to pick on them. You can apply this to game playing. So you may have heard of AlphaGo, which was able to beat human players. And what's the machine learning part of that? There's a big system, but the machine learning part is recognizing a board position and then mapping that to how good the move is. So it's doing pattern recognition on the Go board. And I don't know much about Go, but I do know that the good players have this sense of the patterns, the geometric patterns, what's a good move. And so looking at lots of games and learning that's sort of the internal key part of that. And so, this was the AlphaGo a number of years ago. Now, interesting from that, a lot of people thought at the time that you could take the game playing ideas and move them to the real world. You could have systems that would learn how to drive based on the same idea by exploring moves and stuff. And it doesn't work out. The game playing world is very artificial. There's a very definite set of rules. It's contained. You move to real robots, real physics, and it's much harder. So we were talking a little earlier, one of the areas where AI is not making as much impact is where there's actual physics involved. And autonomous vehicles would be in that class, but also just real robots. Even doing something simple like picking up a glass of water is hard for a robot. So you see more with images and digital things than you are with actual robots. Okay, let's talk about language, because this is the hot topic, of course, everybody wants to talk about. And so let's just take a simple example of how we as humans generate sentences. So it's very sequential, and this is the way that the machine learning models also do it. So the dog jumped over what are we going to say next? Well, there's maybe a person has 50,000 words in their vocabulary, more perhaps that they know, and here's a whole bunch of words that they might use. Some of them are incorrect grammatically, but theoretically they could come next. So let's say the word fence gets picked, and you keep going. So you're generating words one at a time based on what came before, and this is one simple way to generate language. In fact, this is what ChatGPT is doing, surprisingly. You might think it's doing something very clever, looking at the whole piece of text. It's doing this one word at a time, essentially. Now, this is not actually new. The first person to really study language models was Andrei Markov in St. Petersburg around 1900, 1910. Very interesting character if you want to read his biography. Like these very smart people, interesting. But these Markov chains were essentially the first language model, and he was doing this by hand, just counting words and letters that came after each other and putting them into a model. So fast forward, actually not a lot happened in that space. I published stuff on Markov models, but we didn't really make a lot of progress until the last few years in terms of getting better. And we said, instead of having sort of a counting of what's coming next, let's put it into a model where we can learn. So it'll look back over the previous words, and it'll try to use the same model that we talked about before, the same type of model, to predict what's going to come next. So what it does is it puts out a probability distribution over all possible words that might come next, conditioned on what has been written so far or said so far. So here we see a few words, maybe the top words, but there's thousands more words going into the ground with small probabilities. And then it will typically sample a word, and that's why you don't always get the same answer. So in this case, it's going to pick the top word, and it's going to put that back in the input and say, okay, now let's go again, get the next word. And that's what it's doing when you're using ChatGPT. It's generating one word at a time. So we get the next word, we get another distribution now that we've learned somehow with the weights. And this time it doesn't pick the topmost word, it picks width instead. And this is found necessary to give sort of human variability. Otherwise you get sentences that are very boring. They say exactly the same thing all the time. So this is why they use the sample from the probabilities. And as I don't have to tell you, but this works like amazingly well, so better than you would expect it to work. So I asked it to write 2 sentences about the topic of my talk, how AI might change scientific research. And it writes something, very sensible. It's actually kind of boring and bland, but, it's if you've used ChatGPT, it's poised to revolutionize scientific research by accelerating data analysis, blah, 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 But surprising that it can do that. So it's taking what I wrote and then just saying, okay, I need to start a sentence. What can come at the start of a sentence? And but it's not using any grammar, any formal reasoning. It's just generating one word at a time with probabilities, which is why and it's built on a vast amount of data, so it can look really good, but it's not really thinking or it's not really reasoning about what it's saying. So keep in mind when you're using ChatGPT in your startup or something, it may do unexpected things. Why does it work at all? So let's take that first part of that sentence, so you get the next word. Well, one of the things I didn't go into, but we go from text to numerical representations of words. So a word like cat or cats or kitten will map to a very similar, called a vector, a very similar set of numbers at the input. And that's actually quite powerful. And we'd known that for a while. Then the internal representations effectively, instead of going back one word or two words, they can go back quite far in the sentence and kind of remember context. But this is all happening not by design. It's just more, this was found out more by trial and error than anything else. And then the other key thing is you train this on all of the internet. And I heard recently a discussion with OpenAI that they're running out of data. There's just not enough stuff for them to train on. So these chat GPT things large language models may saturate. But they're trained on billions of words. You need a lot of data. And again, you're using that calculus idea of iteratively adjusting the weights. And here, we don't need anybody to label images of cats and dogs. We just need text, because you're just predicting the next thing. So it's very easy to get data to train these things. Now, we're going to take a jump. Everything I've said so far, even this language model, ChatGPT being an example, is really a classifier. It's saying what might come next out of a finite number of things. There's a certain number of words that could come next, so it's always predicting one of k things, what word might come next. A different idea that's related is what are called generative models, where on the output, we're going to generate not just one of k things or some probabilities, but maybe an entire image. And so many of you have seen this kind of thing, where we take, say, input text, and here I just asked for a dog on a surfboard, and I got a dog on a surfboard. You have to kind of stretch your imagination a little bit, but the models I've been talking about, we can configure them with images and text to do this with some cleverness. There was definitely some cleverness here. I mean, then you can do things like take sequence of images, for example, weather images, and say, well, just like a video, you say, well, here's what happened the last hour, the next hour, the next hour, and you have tons of data to do this, and keep asking it to predict the next image. So now the input is a sequence of images, the output is the next image, and you adjust the weights until it gets it right. All right, how are we doing on time? We're all right, nobody's burning out the door. All right, okay, so at this point, I've given you a very high-level picture of AI and machine learning. And the ideas that you saw are in most AI products and systems out there. The companies don't always advertise that they're using calculus and stuff like that. They want you to think it's magic and they invented it, but in fact, these are, the engineering is very impressive, but there's a lot of basic mathematics behind it. Okay, so for science, it's good to think of context here. I mentioned, things were happening back in the 80s and we didn't have enough computers. And again, we were talking a little earlier, in this graph here, this is showing time here, and the y-axis is log scale, and it's showing internet connection speeds, it's showing disk drive price, dollars per megabyte, transistor price, you can think of that as computing price, and it's going down, it looks like a straight line, but it's actually on a log scale. So that, I don't have to tell you this, but all of this stuff has got really cheaper, and you're an audience I like talking to, because when I tell 20-year-old students this, they're like, really? You guys only had 64K for your memory on your computers? How did you do anything? I'm like, you believe me, right? If you were back here in the 70s and 80s, it was hard. You had to think about it. Now, memory is almost free. So, yeah. Okay, so that's happened. And then there's been a revolution in sensors as well. Here I'm looking at Earth types of sensing, so satellites, UAVs, LiDARs, and things on animal sensors, and then stationary sensors. This is just for ecology, which I'm going to talk about in a few minutes, how AI is impacting that. So you have, all of a sudden, all the scientists have new kinds of clever sensors, and they're very cheap, and they can put them everywhere, and they come and beat, a path to your office and say, I've got a billion data points. What can I do with it? You're a machine learning guy. And you sit them down and say, well, let's see what we can do here. Now, AI in science, there's a few different roles. In trying to think of how to talk about this, I thought, well, how does AI impact science? I think the first one that I'll talk about is classifying. So we've already seen classifiers. We can classify cats and dogs, in theory. Let's see how that works in scientific applications. We've seen how to generate new things, and climate predictions, protein structure, this is where the generative models are getting used, where the outputs are structured and like images or have some spatial structure to them. And then the third one, I won't say much about, but I think is really interesting, which is, could AI programs help make breakthroughs and develop new knowledge? We're not there yet for sure, but that's an interesting question. We'll come back to it in a few minutes. So let's start with classification. So scientists loved order in the world. They're like, okay, we understand this, let's put things in buckets. So they like to classify things. This is Carl Linnaeus, and in his 1758 edition of his famous book, he had the world divided up into 4,400 species of animals, 7,700 species of plants. And science likes this, and there's taxonomies and order and hierarchies and so forth. So classifying things shows up all over the place in science. And astronomers were among the first people to really latch on to AI. And I guess you heard James Bullock talking. So they're forward-thinking folks. And typically, they might have lots of images of the sky, and they want to know, is it a star or a galaxy, for example. And graduate students in astronomy in the 60s, 70s, 80s had to do this by hand and derive catalogs, and it was really time-consuming. And so they much prefer to have this pipeline now where they replace the human with a model, and you can take all your sky survey data, feed in the objects, center your image thingy on them, and get out, what type of star a galaxy is, and then put it into a huge digital catalog. Now, I'm fortunate in my career that I was sort of in the mix when this was happening. This is JPL up in Pasadena. Some of you might recognize it. And I worked there along with my beautiful wife in the late 80s, early 90s. And there was a lot of excitement about gathering data from spacecraft. So one of the first applications I got involved in was counting volcanoes on Venus. They had all these images of Venus from the Magellan spacecraft, and there was too many. They just couldn't go over them one by one, and they wanted a map of where the volcanoes are. Venus has lots of volcanoes. And then you also had the astronomers. They were down at Caltech mostly, and they were like, hey, we got tons of things we want to classify too. So myself and my colleague, Usama Fayyad, and many others, this is a paper I was looking at. It was fun to look this up. This was 1996, and we were talking about doing this in an automated way to create catalogs. And I realized now we were too early. The computing and the data really weren't there to support this. And people were actually telling us, this won't work. Yeah, you should do something else. How about that other job that you could do? I'm like, no, I think this will work. I'll just have to wait 10 or 20 years before machine learning becomes cool. It did. So hang in there if you're. And astronomers latched onto this in a big way. So modern astronomy, this is just part of their routine. Yeah, machine learning is part of the pipeline. This is out in New Mexico, the Sloan Digital Sky Survey, one of their telescopes. Goes through neural networks. They classify it, make all kinds of predictions about what types of galaxies there are, and gets put in a huge database that then people all over the world can log in and do science on. So this is a very, very nice application of where AI is directly helping. And instead of a few grad students trying to do this and getting maybe only a few hundred objects, they can have millions and really understand what's going on in the sky. Now, if you remember back when we were doing cats and dogs, and it's the same with stars and galaxies and variations, we need labels to train the models. We need to tell the model what's the right output, what's the wrong output. And so citizen science has played a huge role here. It's really interesting. Zooniverse is a nonprofit of the University of Oxford and some other places. They have a whole bunch of citizen science projects where people just go online and use their own eyes. There's sometimes a little bit of training, and then they label things, and then these get fed into training machine learning classifiers. eBird, if you're into birds, is another one where people take pictures of birds and they label them and they build machine learning models doing that. NASA has its own one. So citizen science has played a big important role in creating the training data for these models. I'm going to focus for a few minutes on camera trap data because it allows me to show you images of animals in funny positions, and it's nice for a talk. So ecology and studying animals has been revolutionized by sensors, and now AI is playing a big role. So this camera trap is basically static cameras that are put out there in remote places. They're They have them here in Orange County up in the hills. So they can see animals in their natural habitat at watering holes and so forth. But to make use of this data, you need to make sense of it. You just don't want the raw images. You want to classify there was a fox at this tree at this time. There were 2 bears over here. So you need to have a classifier. And again, they build catalogs out of these using machine learning models. So here's one for panda bears. And it's going to move kind of around the image until it finds something that looks like a panda bear. And it works pretty well. This is all pandas. And of course, this is a bit cherry-picked from the paper. They show lots of good examples. It can detect 2 pandas in places and so forth. And so here's another example, and it's fairly impressive what it can get. These are all correct classifications, different kinds of lighting. So these things are now widely used. There are incorrect classifications. These models all make mistakes. And these ones are somewhat understandable. There's bad lighting or some kind of blur or something like that. We're going to talk a little bit more about mistakes in a few minutes. I had fun making this talk because I was able to look around and see, wow, people are using it for sharks. They're using it for every kind of animal and even plants that you can think of. So here's shark detections underwater, looking at plants, also looking at the sizes of the plants as they're growing, looking at the pose of animals. There's a lot of stuff you can do. And then the scientists use these catalogs of time and when the animals showed up and which ones were together to figure out behavior as a function of time of day, low density, high density regions, where the animals range, how far they go, stuff that they couldn't do before. So and AI is playing a key role in that pipeline of helping to classify things. And as you get more data, so the x-axis here is training images, the number of labeled images we need to train the model, you get higher accuracy. It's not quite at 1 yet, but it's relative to humans, but it's getting a lot better. Now, one thing to notice, the x-axis here is again on what's called a log scale. So we're going from 1,000 to 10,000 to 100,000 to 1 million. And what that means is that to get a small, that last 0.05 of accuracy that we want to get close to 1, very hard to get. You need massive, massive amounts of data. And so, yes, you could build these models, but there's a need for data. And it might flatten out before you get to 1. It just might not be possible to get as good as humans on some of these tasks. So here, for an example, is incorrect shark detection. So the authors of this paper were upfront enough to say, hey, here's things that where the model doesn't work. And you can kind of see, like, for example, up in the top left is a picture of a shark. And this is a good example because a human would say, well, it's not a shark, right? We were looking for real sharks. But the model doesn't know this. So this is an example of common sense where an AI model, a machine learning model is, it looks like a shark, but it's not understanding the context. There's also a dolphin there. The other thing to notice here, and this is very common and a real problem that we haven't been able to solve in machine learning, these AI models, they're not only wrong, but they're very confidently wrong. Now, we all know people like this. But this is 0.96, 0.97. Damn it, it's a shark, and, well, excuse my language, but anyway, that's the neural network talking there. All right, this is a common problem, all right. And the other thing, I suppose, is that it makes errors that humans, if you look at the ones that humans get wrong relative to other humans, say a committee of shark experts or something like that, humans tend to make different kinds of mistakes than models, which is interesting. I think I'll skip this in the interest of time. I want to point out that, again, let's say we're now satellite data from NASA. NASA has been creating these global land cover maps and all kinds of other maps that scientists use routinely, and they're using machine learning models, AI models, to do this. And they've been doing this since 2000, if not earlier, routinely. So AI for science is not new. It's actually been around for a while. It's been accelerated. So this image, it's a little hard to see what's going on, but it's switching between 2000 and 2020. And if you look at the dark green up in the top right, up in Siberia, or you look at the dark green down in the Amazon, you'll see differences. So and these are actually pretty large scale. So if we focus in a little bit more, hopefully this will oscillate here. Waiting. Well, it's supposed to show you the Amazon is shrinking. It didn't. Hopefully this will show you, okay, it's showing you that this is pretty dramatic for built-up areas in China between 2000. But driving this is, every pixel or every few pixels that the satellite's picking up is being classified. Is it a forest? Is it a building? Is it grassland? And a human couldn't do this. So this is really derived. NASA, setting up all these satellites, get all this information, but AI makes it kind of useful to people. And this is all going on, has been going on for quite a long time. Here's a project at UCI with a really good colleague of mine, Jim Randerson, and a researcher, Yang Chen. And we're trying to learn It's showing. Okay, so this is a fire from the creek fire from a few years ago, and we're trying to use machine learning now not to just predict a single number or a single class, but learn the dynamics of fires. So we have unfortunately, lots of data from fires, from satellites and so forth. And can we learn models that can predict what's coming next? Using the same ideas I talked about before, but now applied, it's an interesting, challenging problem of how to do this. And this is showing the fire growing over time. Just hot off the press, yesterday, I had to update my slides. Weather forecasting. So the way weather forecasting has been done traditionally is to build physics models, simple models of physics in 3 dimensions, and then run them forward in time. So lots of fluid mechanics and things like that. And they've gotten better. The finer resolution you can get, the better they get. But running things in 3 dimensions over the whole globe is very computationally expensive. So it's always been, these numerical weather models are state of the art, but they're you need a whole bunch of really expensive physicists running the things, and it takes a lot of computer power. So DeepMind put out a paper where they showed they could do this with machine learning. So they show it sequences of weather images, and it predicts what comes next. And after a lot of work, I mean, they had a lot of people work on this for quite a while, it can do a little bit better than the best of the numerical weather models, which is a little surprising that they could do this just with machine learning, a black box. So it takes in the current state, it gets a 6-hour forecast, and then it feeds that 6-hour forecast back into the model and keeps doing that 6 hours, 6 hours, 6 hours to get a 10-day, 12-day, 15-day. They have about a 60-page paper in Science from yesterday, if anybody's interested in reading it. Lots of details, quite interesting. But if you read it closely, you will realize, and they don't really advertise this, that it actually needs the numerical weather forecast as an input. It's not working on its own. So, they kind of advertise this, yeah, we can get rid of expensive numerical weather forecasting and do this machine learning thing, but that's actually not true. Now, I think this will go away eventually, but it's another example of where, kind of the advertising for machine learning is running ahead of the reality a little bit. And so the numerical weather forecast is still very important here in this work. A few years ago, DeepMind also address this problem of going from 2-dimensional or 1-dimensional protein sequences to 3-dimensional structure. Why is this important? It's really important for drug design. You want to be able, we can get protein sequences, but we don't know what their configuration is like in 3 dimensions. That's expensive to do, hard to do, but very important for various therapeutics and so forth. They took known mappings that were done with expensive instruments and tried to use a machine learning model to learn the black arrow, and were successful in doing this. And so they beat all the previous machine learning models that were doing this by quite a margin. Huge excitement, they got a lot of publicity. But if you look 2 years after this came out, or 2.5 years, 3 years, I guess now, this just came out a few weeks ago. This is in Science or Nature, saying AlphaFold was touted as the next big thing for drug discovery, but is it? Getting these things to actually work in a pharmaceutical setting with labs and all the things you need to do, it hasn't quite lived up to its promise. And so again, a huge amount of interest. So kind of like a lot of new technologies, I guess, huge spike of interest initially, and then it settles down to something, how useful is it really going to be? And where it settles down to, sometimes can be a little unpredictable. So definitely very cool, but didn't revolutionize drug design the way people thought it might at the beginning. All right, we've looked at classifying. We've looked at generating, we've looked at the climate predictions. Let's say a little bit about discovering, which is really, really interesting. So AI and scientific discovery, what might that look like? Well, let's think about what scientists do. And I'm an engineer by training, so I'm not a scientist, but I'll talk about science anyway. So if you think about on the left here, it's kind of the routine lab stuff where, yeah, we got to sequence this protein, we got to do this, we got to do the other thing, and you're building incrementally on what's known. Very important. That's most of what scientists do, 99% of it. The other is the inspiration, if you like, the breakthroughs, the real discoveries, the change of paradigm. And there's, I just show a few texts here on that. So what we've seen up to this point is largely for the left-hand side, where AI can get into the pipeline and do things that would take humans a long time to do, or do things humans couldn't do. But it's essentially in this, kind of regular scientific exploration mode. On the right-hand side, you can ask the question, could AI, with language models and with a lot of data, start coming up with new hypotheses, new things that we haven't thought about? And scientists get very excited about this, like, I could get a Nobel Prize if I can, prompt ChatGPT the right way. Well, okay, now this is not a new idea. In fact, in CMU in the 1980s and even earlier, AI researchers were thinking about this. And they were thinking more in terms of rules and procedures and so forth. This is a picture of Herb Simon, who won a Turing Award, which is the top award you can get in computer science, really hard to get. Also a Nobel Prize, so he was a smart guy. And he was thinking about this. He worked with somebody called Pat Langley, who actually came out to UCI in the 1980s. UCI was very big in machine learning, and continued to work on this. And I realized I was kind of mixed up in this as well. I edited a book called Advances in Knowledge Discovery and Data Mining. So there was a whole bunch of activity 20, 30 years ago on could we not just collect a giant catalog of stars and galaxies, for example, but could we then run another program that would go in and look for interesting patterns and say, aha, here's a new type of star that we haven't seen before. What we learned, essentially, is that this is really hard. And as computer scientists, we were like, oh, this can't be that hard. And part of the difficulty was representations of knowledge. What do people already know? So what we found with these programs were they would find all kinds of stuff that we already knew. Like millions of rules and patterns and things, and you're sifting through it going, where is the interesting stuff? So these programs didn't have any way to really measure what was interesting. And one way to think about this is a knowledge gap. And in particular right now, if we think about it, human scientific knowledge in the sciences at least, it tends to be explicit. It's written down, it's papers, it's equations and so forth. But the AI knowledge that we're generating with these models, the neural networks that I showed you, these mappings, it's really inside internally in these models, those weights, those patterns. And as I've showed you one or two examples, they're really hard to understand. So getting, if you like, the knowledge out of these models, they're really black boxes, and it's very hard. So there is this gap now between what the models are doing and what we can write down, what's known theory. And so, for example, the weather forecasting one, they're very interested to try to figure out what is it doing differently to the numerical physics-based weather forecasting. But it's actually really hard to figure out that difference. And that's going to be a big challenge going forward for AI and science, I think, particularly on the discovery side. And so you can think about how could we maybe bridge this gap. I'm going to tell you a little bit about some work we're doing at UCI. This is with an excellent colleague, Mark Stivers, who's in cognitive science, where we're not addressing this problem head on, but we're looking at what would, if you had a human scientist and an AI assistant scientist, how might they collaborate? And this has become quite a hot topic, not just AI on its own, but humans and AI working together. How should that work? What are the principles for that? So we do experiments where we have people classify things, and then they can indicate their decision, and the AI agent, which is a neural network model like we saw before with the cat, is generating probabilities of different things, and the person can either ignore it or they can start taking its advice. It allows us to study different ways that we can present information from the AI and how quickly do humans pay attention and not pay attention and help us design these things. And so there's a tradition in wisdom of the crowds of multiple people are better than any single person in forecasting and making decisions. And so if some of this is like wisdom of the crowds with a human and an AI. And one of the interesting things we found in work about 2 years ago is if on some of these image classification tasks, if you want to get a second opinion, you're actually better off to go to the other type of agent. In other words, if your doctor is a human, then the second opinion should probably come from an AI. It's actually better than the doctor. And similarly, if your doctor is an AI in the future, don't go to another AI, go to a human for your second opinion. So, there's a lot of caveats with that. Read the paper, but interesting things. So this brings up a number of questions at the human-AI interface. How should AI models communicate to humans? Right now, they don't really communicate, despite what ChatGPT looks like. When should a model intervene? When should it make suggestions? Anybody remember the Microsoft paperclip debacle? Yeah, it was horrible. So you don't want to do that. Interesting sort of conceptual ideas here. Theory of mind. We think of people, theory of mind, do I understand what your goals are, what you're thinking, what you want to do? Well, now we have models in the mix. So we can have humans, do they have theory of mind of a model? And does the model can it develop theory of mind of what the human is trying to do? This might sound a little far-fetched, but it's actually one of the interesting ways to think about how you get humans and AI working together. And instead of designing AI systems kind of completely on their own, no humans in the picture, there's an interesting angle of research now looking at how do we design AI systems to complement what humans are doing rather than to replace humans. So the whole training of the model is assuming that there's a human already there doing their thing, and the AI is just to help. So for areas like autonomous driving, this is actually quite important. And another thing that's interesting here is that this is likely to require more than confident computer scientists running around doing this stuff. Social scientists, cognitive scientists really can play a role here. So again, National Science Foundation is leading a lot of this research and funding it, and the human AI interface is a very exciting area research-wise. All right, I've mentioned some cautionary notes, and I think we're running out of time, so let me try to wrap up here. If you don't believe me already that you have to be a little bit careful about AI and it can make mistakes. Let me show you a few more examples. So, AI can be unpredictable and non-intuitive. So let's show an example. So this is from a few years ago, a machine learning paper. We have let's say a standard classifier. You give it an image of a pig. It says, this is a pig. So the input's a picture and it says it's a pig. You change the model just a little bit. Now you change it in a sort of a clever way, but you add essentially random noise. You get a new image over on the right. Everybody in the room, right? What is it? It's a pig, right? Another pig. Anybody disagree with that? It would be interesting if somebody said this. All right, you give it to the algorithm, and it classifies it as an airplane. And you can come up with hundreds, thousands of these examples. It's just a fundamental feature of that mathematical function. We're just shifting the weights in a clever way to get it across a decision boundary. What this tells us is that the way these models are doing their classification is very different from the way humans are doing it. And those internal representations that they have are probably not mapping to what we're doing. So this is, interesting. What other things can happen? Well, AI can hallucinate, hallucinate, make things up, so particularly with language. So I asked it to generate a plausible abstract for a scientific paper that describes the addiction of small panda bears to French fries and TikTok, and how this is causing them to fall behind their education. So complete nonsense, but our students at UCI are now doing this kind of thing and saying, hey, I can submit a paper on this and see if the professor even reads them and notice. So not only did it give me an abstract, it gave me a nice title off the bat, really scholarly sounding title with even the Latin name for panda bears. I'll let you read that. And then it goes on, and it gives me an abstract, and if I'd asked it to write a whole paper, it would have happily done that. The last sentence, the research employed a comprehensive mixed methods approach, combining behavioral observations, dietary studies, and cognitive assessments of young panda bears within controlled captive environments. It sounds very authoritative, and this is one of the problems. This is complete nonsense. Now, full disclosure, and I didn't include the slide, I asked it then, do you really believe this? And it responded, I made this up. So one of the things OpenAI is doing with ChatGPT and other language models that other folks are developing is they're doing a lot of manual engineering to try to defeat professors and grad students who come up with examples like this. So it kind of is wary of stuff we're doing. So this is a big deal now in science because how do we know that a lot of papers aren't just being written by ChatGPT and you can easily write a paper? So is it any good? And so a lot of journals and so forth are now banning the use of AI. So Nature said ChatGPT is fun, but you can't have it as a co-author on your paper. And none of the paper can be written by ChatGPT, which is a little extreme because you can use grammar checkers and things like that or spell checkers. So where do you draw the line? So it's going to be very interesting for science to see how AI enters. And I have no doubt that even the last few years that there's quite a few papers out there that were written by AI programs. I'm certain of it. I've seen them. And so that's going to be, you talk about fake news, well, get ready for fake science as well, or more fake science than we've had before. Meta, that well-known responsible company up in the Bay Area, developed a scientific language model before ChatGPT, and they pulled it within a few days. It was a disaster. And just to show, people have come up with, before it got pulled, so the number of giraffes that have flown on a lunar mission is currently, and it was prompted, what does it say? Well, it says the number of giraffes that have flown on a lunar mission is currently 28, okay, including 15 on the moon and 13 on Mars, of those blah, blah, blah. And you're like, so it doesn't know what it doesn't know. It's a big problem. Okay, so then, this just came out a few weeks ago in a Nature Medicine saying, okay, well, large language models, aren't knowledge-based. They don't know what they don't know. They get the facts wrong. But let's use them for reasoning instead, because there are impressive demos. Some of you have seen them where you give them word problems like, SAT-style problems with math and so forth, and it does surprisingly well. So I sat down with ChatGPT just for this talk, just for this audience, and said, okay, can I find a simple example where I can fool it? Now, they're wise to this. They've fixed it up, but I found one. So I said, my birthday's in July and my sister's birthday is in May, which is true. And which of us is older? Now, you don't know which of us is older, but ChatGPT was very happy to confidently come back and say, well, your sister is older than you because her birthday maybe comes for July, and therefore She's older. Well, she's not. She's younger. She's 5 years younger than me. And, but this is just an example of they lack common sense. And you can make fixes, and maybe you can make enough fixes, but it's not inherent to these systems. I think we've said most of this. Inherent uncertainty means that for things like weather forecasting, there's things we're not measuring. There's going to be some inherent uncertainty in the system anyway. So AI can help, but it's not going to entirely solve the problem. Another one might be treatment for medical conditions. There's a lot of external factors, environment. I think this is telling me to stop. Blah, 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 blah. Yes. And so I think this is probably a good point. I think you got the idea. Okay. Is there an AI running here? Probably, yes. Okay. AI can overfit the training data, and it gets correlation but not causation. So this is actually my second last slide. You'd be happy to know. And radiology is one of the areas where people have said, oh, AI can be really useful there. In fact, a famous AI colleague of mine, Jeff Hinton, came out and said, there will be no radiologists in the future. It'll just be AI. Well, the radiologists say, no, there'll be AI plus a radiologist. The radiologists need to know how to use AI. But even there, it's a good application area because it turns out like 2 billion radiology images on the planet taken per year, and there's far fewer radiologists to look at all of those. So there is a need for especially in areas that don't have a lot of trained doctors. But so here's one successful example where it got very accurate results, blah, blah, blah. And they went back and tried to figure out what was it really focusing on. So the red areas are what it was focusing on. And they found that it was the success of the classifier, it was detecting tubes. So it was looking for collapsed lungs, which is hard to tell from these X-ray images. And it was detecting tubes. So in other words, people already had the lung collapsed, and the tubes went in and said, aha, if there's a tube there, they must have a collapsed lung. But that's no use if you're trying to diagnose this. It was just correlation. So this stuff is going on. It doesn't get as much publicity as a lot of the other stuff, but just you guys know now to watch out for. So, all right, wrap up. You'll be happy to hear. So current AI, we talked about AI in the big picture. A lot of it is based on machine learning because it works, and the classical AI, it's hard to get it to work. You have seen impressive results across different scientific disciplines. There's no doubt it's useful. But be aware these methods have limitations and blind spots. Thank you for listening.
Thank you very much, Park. I think nobody was anxious for you to end. That was very fascinating. And probably my scariest takeaway is that the internet isn't big enough to feed these things, and it's going to run out of data, and it's going to have to generate its own data, and then God help us all.
That's actually a real worry.
I think when it starts feeding on itself, that becomes a real problem. Okay, they're going to be setting up coffee for us for afterwards, so we have time for a few questions, and we'll have mingling and discussion afterwards. So why don't we go ahead? So I saw a hand somewhere in the back. Over here.
Does AI have any application for, do you think AI has an application for reducing racist and false information on social media?
Yeah, it's a tricky one. I think it could, but I think there's other factors that probably mean it won't, get used that way. I guess I'm just saying the economic incentive for companies to really take this seriously. Yesterday in the paper there was about fake reviews, so similar fake information, and companies have formed a consortium in Washington, D.C. to address this, which means they're going to do nothing, basically. So, I think AI could actually help with that, but it would take concerted effort, probably by a nonprofit or a government agency to really make it happen. Don't know if that answers your question or not, but.
So go ahead.
So maybe to follow up, there are academic papers that show this can be done. It's not trivial because it depends on your perspective. So detecting toxicity, what might be toxic to one person might not be to another person. But that work has not, it's maybe not that easy to make money off of it. So, so I think it's doable, but there needs to be also the will to make it happen.
I had one question about, let me just very quickly, are you doing something at the Center for Machine Learning to bring more interdisciplinary research into that? Is UCI organizing around this? Because you say it's important that you bring the disciplines together.
Yeah, so we started that center about 15 years ago, and right from the get-go, we have cognitive scientists, we have psychologists, we have mathematicians, we have people from the law school. It's centered in the computer science department. We don't think of boundaries. UCI is actually very good that way. It's a young university, and so we don't have these walls that sometimes get set up. So, yeah.
Okay. Saw some other ones. Now you're getting going. Go ahead.
Question here.
I just have a technical question. So all of this requires code, and I'm wondering, is there a common code used to write machine learning, or does machine learning write its own code? Or both?
Let me answer both. So a lot of the success, one of the success factors that I didn't mention was open source code and things like GitHub, and people use Python a lot. It's not my favorite language, but that's what people are using. So sharing code, a lot of open source code, that helped a lot with the development of these ideas. Writing your own code. So going into these language models, they also take data from code repositories, software repositories, the public open source code. And so if you give it pieces of code, it will finish code, and it's actually quite good. And this is one of the application areas where they think as an assistant to people writing code. So writing its own code to do its own thing. Right now, we're asking it to complete code, but it's kind of generating data that feeds back into itself. I'm not sure where it would end up, but yeah.
There was another question. Kunge?
Energy utilization in cryptocurrency is extremely high. What is it in AI?
Yeah, good question. So building something like a ChatGPT actually has a measurable impact on the carbon footprint, of the planet. Universities can't build these models anymore, so only OpenAI and Google and a few places can build something like ChatGPT on that scale, and it requires massive amounts of computing. And there is a branch of, particularly in academia, of researchers who are trying to say, look, we don't need these massive. This is brute force, and it's actually, actually has a carbon impact. Can we build much smaller models that do the same thing? And there's some success along those lines, that if we think about it a bit more, and I'm constantly telling my grad students who are constantly asking for bigger machines, I'm saying, no, let's not use our budget on that. Go back and pencil and paper and figure out how to do this more cleverly with less data and less computation. So, but these things, again, not talked about that much, but in the academic literature, you'll find papers that calculate. I think, like I saw, training one model, and these things have to be trained many times for various reasons. It's like flying an airplane to the East Coast and back again many times. So you can come up with some nice analogies of, how much.
How bad it is.
Yeah.
I have a question here.
Do you work with Esri out in Redlands at all?
Esri?
They do mapping.
Right. One of the images I showed, I forget which one, I think came from Esri or some version of my slides. So yeah, they're one of the companies that has been doing this for a long time, taking satellite data and producing, interpretable information maps and so forth that people can then build on. So they're in Redlands.
Right.
Yeah, seem to do a lot of cool stuff.
They're now mapping the habitat of wildlife. And in doing that, it seems like there's a lot of information that comes in that needs to be reviewed and then refined. And it's exactly what you're, I think, talking about.
I'm sure they're using some of the types of ideas I talked about, yeah.
Okay, we're going to cut it down. We have one more here, back here. Thank you.
Hi, thanks so much for the lecture this evening. This is really insightful. I'm here with a group of buddies, and the common denominator for us is we all have toddlers at home. And so I think we've actually been thinking a lot about AI in the context of just what does it actually mean to learn something. And there's a lot of parallels in raising a toddler. It's a lot of iteration and to kind of eventually get to the right answer. But I think we'd all find it very difficult for them to get to the right answer without a system of rewards and consequences. And rewards and consequences don't resonate without emotion. And so I'm wondering, is there any effort afoot to introduce emotion into these models in order to help them get to the right answer?
I think short answer is I'm not aware of anything like that. I think the analogy with toddlers is interesting because you don't have to show your toddler billions of cats and dogs for them to learn what a cat and a dog is. Or if you take them to another continent, they can still see cats and dogs, and machines are not that robust. So 5-year-olds are still better than a lot of these algorithms. Imbuing, there is notions of reward, actually. The technical details of these things, there is actually a technical term called reward in like the AlphaGo system. It's all based on reward and losses and so forth. So we do penalize our neural networks economically, or at least metaphorically sometimes. Emotion, I don't know. That's an interesting one. I think the human AI aspect, we'll have neural networks that will fake emotions. In fact, ChatGPT can do it already. It's not real, but then are human emotions real either? Some of the time. Yeah, who knows? Yes.
Yeah, I think I heard about a ChatGPT about a year to 2 years ago. Oh, thank you. In your opinion, over the course of the next 3 to 5 years, will AI do something significant for us humans? Can we expect solutions to big problems arising out of AI?
Well, one of the things I've learned from machine learning and prediction over the years is that prediction into the future is very hard. So that's my way of ducking your question. I think there's the potential for, and I'm going to speak as an academic here, there is a potential, I think, for more harm than good, potentially. I see, for example, education, K-12, getting very excited, at least some administrators and school boards and things, bringing AI into the classroom, and isn't it wonderful? I worry that, I still tell my graduate students, just get a pencil and paper and write down what you know and figure it out go away from the computer. And I do worry a little bit that I was talking with Krista, my wife, the other day about the Industrial Revolution. Most of us lost the ability to do stuff with our hands. We now have machines, bulldozers, et cetera. One thing about things like ChatGPT is that we could lose the ability to think independently and reason, and everybody will be relying on, I'll just look it up on ChatGPT. It's almost, So I've gone off on a tangent here, but I do worry about education and the impact of these models if it's not carefully thought about. I'm not an education researcher, but it seems to me that about 6 months ago, I was asked to sign a letter of the existential threat to AI. A lot of academics signed this. I was one of the people that signed it. I didn't sign it because I thought robot soldiers were going to come up the driveway in 3 to 5 years. I did sign it because I think it may have a very negative impact in areas like education. And there's we need somebody sitting back and who has no skin in the game, saying, okay, what might happen here? What might cause? Rather than just throwing this stuff into classrooms, which is kind of what I'm starting to see now. And yeah, as a professor, I want my students to come in and be able, they need to know maths. They need to know how to think logically to design these systems. If we hand that over to machines, well, sorry to end on a negative note, but yeah.
Elementary school students can't do cursive anymore because it's all typing, so they're really having to go back.
This is a problem. Okay, this is obviously outstanding talk. We'll have one more in the back here.
Thank you so much.
Congregate and ask more questions, okay?
Okay.
Thank you.
Yes, I'm job searching, and the first stage was an audio AI interview. So I'm just curious if you can give me some insight what they were looking for. Was it tone of voice, like a lie detector? And then additionally, I had to sign off on privacy, which was a concern for me. So I'm wondering if you can address those issues. Thank you, Professor.
I should have asked this before answering other questions. Is this being recorded?
I see a video camera in the back.
Yeah. I think you should assume that there may be nefarious things going on in terms of all of the things you mentioned. And you can analyze voice patterns for emotion, so they throw a question out and see what kind of response it gets. They can look at your facial patterns. And what's kind of the bad part about this is it can be wrong, as we've seen in some of the examples. So it's quite possible that your data was being analyzed, by some AI algorithms. So hopefully you'll get a person at the next round, so.
Okay, let's give Dr. Smith one more round of applause. Thank you so much. And please, let's all go enjoy some coffee, and I think there are cookies. And we can continue the conversation.